Alright, next part. Here we go, number 11. Three blocks A, B, and C of masses 1, 2, and 3 respectively are initially at rest on a frictionless surface, as indicated in the figure above. What force has to be applied on block C to accelerate the three blocks 2 meters per second squared? Well, if this is frictionless, then you might as well be pushing a 6 kilogram block. The fact that these are separated really makes no difference at all. You could make separate force diagrams for them and do the equal and opposite things, but what it all boils down to is you're pushing 6 kilograms. So force is equal to mass 6 kilograms times acceleration. It's going to take 12 newtons to do that. An electrical motor provides a half a watt of mechanical power. And remember that a watt is joules per second, so that's half a joule per second. How much time will it take for a motor to lift a 1/10 of a kilogram mass at a constant speed from the floor to a shelf that's 2 meters above the floor? Well, lifting at a constant speed, that means that our motor is going to be balancing gravity, right? So the tension force will be equal to gravity, the force of gravity, rather. So let's see, that's mg. So mg, I'm just going to use g as 10 here for shorthand, so that means my force is going to have to be 1 newton. I need 1 newton of force to lift at a constant velocity. Okay? How much time will it take? So I have power is equal to, in this case, I'm going to use the power is equal to work divided by time, since I'm going at a constant velocity here, right? So power, half a watt, is equal to the amount of work done. It's a constant force of 1 newton, so force times distance is 2. Force, 1 newton, times 2 meters over t. So t, if I move that there and that there, t 2 over 4 is equal to 1/2. So it's going to take 4 seconds. That's E. A lot of E's, huh? E's and D's. Number 13. A block slides down from rest with negligible friction down the track, descending a vertical height of 5 meters to a point P at the bottom. It then slides on the horizontal surface, which has friction. 0.2 is our coefficient. How far does the block slide on the horizontal surface before it comes to rest? This is an energy problem. Here, all of the energy is gravitational potential. Here, it's all kinetic. And then it is all tapped out of the system, the work done by friction. So, we didn't lose any energy to here, so that means that the mgh here must be equal to the work done by friction. That's the frictional force times distance. Frictional force is constant, so force times distance. Just like this. So energy is equal to that. That's the work done, right? That work tapped all the energy out of the system, and that's all the energy that we had to start. So mgh is equal to, the force of friction is equal to mu times the normal force. The normal force is mg. And we want to find that distance. The mg's cancel. So I have 5 here equal to mu is 0.2 times d. That's 1/5, so 25 meters. Another E. Are you kidding me? Wow. Look at that. Number 14. The graph above shows velocity as a function of time for an object that's moving along a straight line. For which of the following sections of the graph is the acceleration constant and not 0? Well, acceleration is the slope of velocity. So if we want acceleration to be constant and not 0, well, here it's 0. Here that's bendy, so that doesn't have a constant slope. That has acceleration, but it's not constant. There's constant slope, it's not 0, and so is there. That's no good. So RS and ST. The velocity of a particle is this. What's the acceleration? The Acceleration is the derivative of that. That's 6t minus 2. Plug in 2. 12 minus 2 is 10. That's for babies. Next problem, number 16 and 17. Let's see, we got an unstretched ideal spring hangs vertically from a fixed support, and a 4/10 of a kilogram object is then attached to the lower end of the spring. It's pulled down to a distance of 0.35 below the unstretched position, and it's released from rest at time 0. A graph of the subsequent vertical position of the lower end of the spring as a function of time is given above. All right, at which of the following times is the upward velocity of the mass the greatest? So this is position versus time. So the velocity is the slope of this, right? So that's like asking where is it the steepest slope. So that would be here or here. These are the places where the upward velocity is the steepest, right? At all those places. So it looks like they're doing that within the first second, so that'd be at 1/4 of a second. Right, that's right there. Number 17. What's the spring constant? Well, that's a little trickier, right? Here's the... You can see that this thing is bobbing up and down over this position right here, right? Up, down, up, down, up, down, up, down, over this position. So if you stopped this thing, or let it go forever and let it eventually come to rest, that's where it's going to come to rest. Down, up. So this is its equilibrium position with the that mass hung on it. So that means that at that position, we have the force of gravity would be equal to the spring force, right? That's its equilibrium position. So the mass is 0.4. I'm going to use G as 10. We're looking for the spring constant, and that happens at 0.25 meters. If you're wondering where the negative sign is, I'm just using magnitudes of forces, right? Those two magnitudes are equal to each other. So K is equal to, let's see, that's 1/4, so times 4, 40, and that's 2/5, so 16. Right. Number 18. Identical net forces act for the same length of time on two different spherical masses. Which of the following describes the change in linear momentum of the small one compared to that of the larger mass? So, identical net forces act for the same length of time. Right? So that means the same impulse. Same force, same length of time. So the impulses are equal. And remember that impulse is equal to change in momentum. So that means the change in momentum is going to be equal for both of these. So which of the following describes the change in linear momentum of the smaller mass compared to the larger mass? They're the same. C. Right? Because impulse equals change in momentum. So same force, same mass. Same force, same amount of time, not same mass. But that doesn't matter. So this is just force times time. And if you're thinking, well, the smaller sphere is going to accelerate more, that's true, but momentum is mass times velocity. So both of those are taken into account. So the impulse is the same on both. Number 19. Uniform thin rod above. We want, what's the moment of inertia here? So parallel axis theorem. I know this is through its center, so that's 1/12 ml squared plus the shift. So the shift is from the center to the new axis. So the parallel axis theorem says multiply by m times the shift squared. And the shift is L over 4. Right, from here to here. It's L over 4 squared. So let's see what we got here. That's 1/12 ml squared plus 1/16 ml squared. Common denominator is 48. That's 4/48. and this is 3/48 ml squared. That's going to be E, our favorite letter. Number 20. A certain one-dimensional conservative force means you have potential energy associated with it, is given as a function of x by the expression this, where F is in newtons and x is in meters. A possible potential energy function. So, I mean, just look at this. Look at this and look at these. That is just screaming calculus. So it's either the derivative or the antiderivative. You just got to remember. So think about it for a second. Here's one of our favorite examples. Spring force is equal to negative kx, and spring potential energy is equal to 1/2 kx squared. So how do you get from here to here? How do you get from force to this? You take the antiderivative and flip the sign, or ditch the negative. So the antiderivative of that is going to be kx to the 4th over 4. Don't forget to lose the negative sign, right? Easy. That's such an easy problem if you just remember that, first of all, let yourself be inspired by the answers there, and then just remember an example to help you direct your calculus. Which of the following is the differential equation? Oh, never mind. I'm going to stop there and do the next in the next video. So they're in tens. Just kidding.